Here's another indeterminate form. If we try to directly substitute 0 in for x, we get 0 raised to the sine of 0. Sine of 0 is 0. 0 raised to the 0. Okay, well 0 as a base means that we're going to get an answer of 0. But 0 as the exponent means our answer is going to be 1. So which one wins? We don't know. It's indeterminate. We have to figure that out. So we're going to go ahead and assume that this limit equals a value y. That way we can do that same trick we did in that last problem where we took the natural log of both sides. Remember that we can take the limit of the log or the log of the limit. Those work out to be the same thing. So the reason we would try to take the log of this crazy thing is because of the property of logs, which means that we can pull this exponent out front. The natural log of x raised to the sine of x is the same thing as sine of x times the natural log of x. So we can try to take the limit as x approaches 0 from the right of that. Okay, well, that's 0. Sine of x is 0. And then natural log of 0. Remember that the natural log function does one of these deals where we've got a vertical asymptote here at x equals 0. So as we approach 0 from the right, this thing is going to negative infinity. So this is 0 times negative infinity. So that's an indeterminate form that we've dealt with a few times. We're going to have to turn this into a fraction. And by doing that, we do that by picking one of these two to take the reciprocal of. Now, I am a fan of taking the derivative of the natural log of x. So I'm going to leave the natural log of x in the numerator, and I'm going to take the reciprocal of the sine of x. That might make our trig a little messier, but it'll make our natural log much nicer. So remember that the limit as x approaches 0 from the right of the natural log of x equals negative infinity. And the limit as x approaches 0 from the right of 1 over sine of x, well, sine of x is approaching 0 from positive values, right? From sine of 1, sine of 0.1, sine of 0.001. These are quadrant 1 values, so the sign will be positive. So 1 divided by a positive 0, basically, is going to give us a positive infinity. All right, so this is negative infinity divided by positive infinity. Doesn't matter that the signs don't match. It's still indeterminate. So that means L'Hopital tells us that this natural log of y is equal to the limit as x approaches 0 from the right of, well, we'll take the derivative of the numerator, which is 1 over x. And we'll take the derivative of the denominator. Well, remember the denominator is cosecant of x. So we know the derivative of the cosecant of x is negative cosecant of x cotangent of x. Well, let's see. So the cosecant of x and the cotangent of x are both functions that have a vertical asymptote at 0. So these are both infinity at 0. This is infinity at 0. So we still have infinity over infinity. So we could L'Hopital this thing again, but I don't want to. This is going to get worse as I take the derivative of it. This is a product. This is going to get worse too. So let's think about it before we jump right into a second L'Hopital. Let's maybe wonder if there's some way we can rewrite this so that we can find some things that we want to take the derivative of. For example, x. So x is in the denominator, so let's drop that down to the denominator. So if we drop the x down to the denominator, we're going to have 0 times infinity times infinity. We don't want that. We want fractions, right? So we're going to go ahead and pull this up to the top. The negative we can put wherever, but the cosecant's reciprocal is sine, and the cotangent's reciprocal is tan. So we've got 0 times 0 over 0. All right. Let's save ourselves a bit of headache and recall that this is an important limit, right? The limit as x approaches 0 of this equals 1. We proved that using the squeeze theorem way back in chapter 1. We also proved it using L'Hopital's rule earlier in these notes. So we don't need to do any more L'Hopital here. We can just say, oh, this is equal to negative 1 times the limit as x approaches 0 from the right of tangent of x. But that's just the tangent of x is 0 when x equals 0. So this is negative 1 times 0, which is equal to 0, which is not your answer. This is where people make a mistake, right? Because they'll say, oh, yeah, I finally got my answer. But actually, we found what the natural log of your answer is. So the natural log of y equals 0. So that means that y equals e raised to the 0, or 1. And that is your final answer. Fantastic. All right, one more L'Hopital example. This one is going to be in the form infinity minus infinity, right? When x equals 1, the natural log of 1 is 0. Coming from the right, we're going to have positive values. So this is a positive infinity. And then same thing with this, right? As x comes to the right, comes from the right, we have positive denominator values. So 1 divided by positive 0 is going to give us positive infinity. So this is an infinity minus infinity, right? We have to check those signs because if one of them is positive and the other one's negative, if it turns out to be infinity minus negative infinity, well, that's not indeterminate. That's just infinity plus infinity, which is infinity. So yeah, this is a positive infinity minus a positive infinity. So this is definitely indeterminate. So how do we deal with this? All right, so subtracting fractions means getting a common denominator. That part doesn't change, but we'll go ahead and get a common denominator, which basically means we're going to multiply by x minus 1 over x minus 1 in the first fraction. We're going to multiply by natural log of x over natural log of x in the second fraction. And then we'll have our common denominator like that. Right? So when we get our common denominator and subtract the fractions, we get a single fraction. And what do we get when we try to directly substitute in here? Well, we get 1 minus natural log of 1 in the numerator, which is 0. And then we've got natural log of 1 times x minus 1 in the denominator, and that's also 0 times 0. So this is definitely a L'Hopital situation, not surprising, right? So the limit as x approaches 1 of the numerator is equal to the limit as x approaches 1 in the denominator, which is equal to 0. So because of our 0 over 0 situation, we can L'Hopital. Sorry, this is getting a little obnoxious, I know. I can't resist it, though. So we will take the derivative of the top, and that will get 1 minus 0 minus 1 over x. And then on the bottom, we get product rule, gives us 1 over x times x minus 1 plus natural log of x times 1. All right, so that's L'Hopital to give us 1 minus 1 on the top and 1 times 0 plus 0 on the bottom. So we still have a L'Hopital situation, right? So we have the limit of the numerator is equal to the limit of the denominator which is equal to 0. So we've got a 0 over 0 situation. But do not jump into L'Hopital again. Remember, the idea is that we want L'Hopital to help us make things simpler. And taking the derivative of the top and the bottom is not going to make things simpler here. So let's try something a little bit different. Maybe if we tried to get a common denominator and simplify this a bit, we've got fractions inside fractions. Let's multiply this by x over x. That's basically the same thing as getting common denominators here. Distributing the x through the top, we get x minus 1. On the bottom, the x cancels out with this x, so we get x minus 1. And you might say, oh, yay, we're gonna get to cancel these out, but we don't because there's a plus here, plus the natural log of x times x, or x natural log of x. All right, does that still give us L'Hopital? On the top, we got the limit as x approaches 1 from the right of x minus 1. That's equal to 0, but then we have 1 minus 1 plus 1 times 0. So yeah, we've got the same L'Hopital business that we started off with, both of those limits. Are equal to 0, so this is still a 0 over 0 situation. All right, but we'll try L'Hopital one more time. This time we don't have quite as much of a mess, I think, I hope, I feel like, because we don't have natural log of x on the top and on the bottom like we started off with. So L'Hopital tells us that we've got the limit as x approaches 1 from the right of this equals the same limit as the derivative of the top over the derivative of the bottom. So this is 1 plus, oh, we got the product rule one more time. We've got 1 times the natural log of x plus x times 1 over x, which is 1. All right, cool. Now, if we try to directly substitute into here, we get just a 0 in this one part right here. So we get the surprising answer 1 over 1 plus 1, or 1/2. And that is finally it.